path, all the edges I use back in the reverse direction, and you can so the crux of the proof of say, once you do find the solution, you got a small. From an algorithm design, optimal. It's not like, say, like, dynamic programming where you just go fill a table, or greedy, right? You just find one solution and you just gradually just pass through your data. It turns out this is a phenomenon that is actually studied a lot in numerical analysis and repeat the same algorithm, but then have your solution gradually come. And I will elaborate on this further. Efficiency challenge. And this efficiency challenge is actually underlies a lot of optimization, the efficiency of graph and matrix. Where there's a lot of flow. Also have a very large diameter. T can be really expensive to find. You just naturally combine get a quadratic time algorithm. So you look at the square time algorithm, which size of a modern data set, this gets cost prohibitive. So it's a very kind of natural place to look for to ask questions and look for better algorithms. And this actually has motivated a lot of work on the MaxFlow algorithm. This was first studied, as Jelani said, by Ford and Fulkerson in 1956, where they gave an algorithm that runs in n² time. Hopcroft and Karp lowered it to about n to the 1.5. And essentially work after that essentially try to generalize this exponent to all the other forms of MaxFlow. So you probably can have heard about things like Dinnick's algorithm. Dinnick's is to get it to work for general capacities. Things like, and then you have min-cost flow. In fact, actually, in programming context, my understanding is that it's actually not clear whether we actually have a codable into the 1.5 code package. But a lot of work after that was to get it more robust. But essentially, the improvement on this most basic kind of exponent didn't continue until about 10 years ago. So 10 years ago, there was a paper by Alexander Madry who showed that you can get exponent down to 1.43 or 10 over 7. So for bipartite matching, he obtained into the 1.43 time algorithm. And then progress stalled a little bit again until about the latest round of development. So the latest round of development really happened about, well, actually exactly 3 years ago. So three years ago, Yang Liu and Aaron Sidford, they archived a paper that does about m to the 1.375. And subsequently, within about 4 months, it became 1.33. And then as of last year, or actually March of this year, the exponent became 1. So what I want to talk about in this talk, the technical content, is I want to talk about this latest development in this topic, which is that given the formal result, this is kind of like the most general form of this algorithm. It says that given any graph, a demand vector, and then a set of convex costs on the edges. So these are convex functions. So it's the overall problem is a convex minimization problem. There's an algorithm that runs in time m to the 1 plus little o of 1. What is little o of 1? It's something that is smaller than any constant. I'll get to what the constant is, but you can think of it as it's less than 0.01, it's less than 0.001. It's smaller than any polynomial factor in m. And it runs in time that times log squared of 1 over epsilon. And it outputs a solution that is a 1 plus epsilon approximate minimizer to this problem. So I want to talk about roughly how this works. And this is very much a theoretical algorithm in that it's really you can think of this less as an algorithm, but more as to prove to you that it is possible to asymptotically solve max flow bipartite matching all your favorite flow problems in time that is m to the 1 plus little o of 1. So it's essentially a proof of concept that this is a problem that can be solved in almost linear time. And there are essentially 4 major components to this. So the first one is that we compute the flow via a bunch of approximate undirected minimum ratio cycles. And then the second one is to use a result by Madry, who says that you can approximate all these mean ratio cycles via what's called tree approximation schemes. And then we show that because there's a lot of these problems, right, we have to make them fast. So what do we do? Instead of having Madry's algorithm as a static algorithm, we make it a dynamic algorithm. So we turn it into a data structure. We turn it into a data structure that's able to approximate the mean ratio cycle in time that's m to the little of 1, so subpolynomial. And then finally, to put all these together, you actually have to study the interaction between the data structure and the inner loop. So some of you may be familiar with how you white box a data structure, things like offline div conquer, this type of ideas. And that's actually how the overall algorithm works. So that's kind of how I describe this algorithm to people working on theoretical computer science. But because I'm talking to a programming competition audience, and notice that as I went on this discussion, I keep on saying the word tree and tree and tree more. I want to give you a slightly different take on the other way you can think about this, which is that where is this efficiency coming from? It's coming from trees. It's coming from the fact that I have a lot of trees. So this is actually, you can actually motivate a lot of this idea, and actually quite a few of the authors on this paper did programming contests. So actually, when we talk with each other, we actually motivated each other with essentially programming contest memes. How many know about the CTSC papers? Okay, I wish it's more well-known, but the general idea is that if it's a meme programming contest, any kind of like idea where there's more than 3 problems, chances are CTSC has done a report about all the possible problems in this category, and this was the case as well. So there actually was a whole like 12, I think it was a 13-problem study by this guy, by Jiang Lun in the Winter Camp 2019, where he actually talked about this whole concept that you can actually speed up min-cost flow algorithms by simulating all the augmenting paths using data structures. So I mean, covers a whole bunch of things, including IOI 17 wiring, includes the Conquer the World problem from World Final 2018, also includes network flow with maintained by tree problem from CTSC 2010. Unfortunately, because it's a short talk, I won't have time to go through the problems in detail. I'm trying to avoid having to go through the problems in detail. But I think his solution to problem 11 sums up pretty well. It basically just says keep comm and tree on. Like, store the things with a tree, maintain with a tree, and just throw more trees at it, and eventually it will work. So quite a few of us actually on the paper actually know this. I'm not sure about other papers, but I'm actually not sure what exactly is the statistic on this, but I was joking with my co-authors, we actually might set the record for the total number of World Finals participation of authors of a paper, in that we have 6 on this paper. If you count World Final, last year's World Final Invitational as well. So a lot of us actually know this kind of like, you can maintain augmenting path, you can maintain flow structure with data structures. But on the other hand, there's actually indeed very major caveats in getting this all to work. In that, if you look at the graph algorithms literature, they are also aware that you can maintain flows using data structures. But a lot of that seems to only really work for planar or like very well-structured graphs. So things like trees, path. So you kind of, in the algorithmic literature, they're known as what's called separable graphs. They're graphs where it's actually possible to cut things apart and so on. So there is, in fact, a very big limitation that this type of approach should really only work for things like planar graphs. And indeed, kind of the direct approach to this. So before we did the general graph one, we actually also had a paper last year in January where we showed that this also worked for planar. So it was, first we had a paper that says that planar min-cost flow can be done in almost linear time. And that one was actually based on far, far more kind of direct mapping of seg trees into like a separable graph. But then what made it work is that the notion is we introduced the notion of approximations and iteration. So kind of the key idea in there is that instead of working with exact problems throughout, as it would do with a purely data structure type of build, what we did instead is we say that, hey, let's introduce some approximations. Let's throw approximations all over the place. So this Madry result actually says that you can actually approximate transshipment or mean ratio cycles via just generating a bunch of undirected trees. And once you're in that setting, it becomes far more amenable to the same kind of tree-based maintenance tricks. And that's actually how the dynamic versions of these happened. And then once all that is happening, because there's some other issues, we actually have to redesign all the pieces to get this whole call stack to work together. And that's essentially roughly how the algorithm works. Any questions about this kind of? How am I doing for time? Yes? Oh, so the question is, how do you get 6 people together to write a paper? Okay. Maybe, okay, yeah. So I mean, it's a little bit of a long question, but the question is, how do you communicate, how do you discuss, and how do the ideas come about? And the answer is very gradually, very slowly. You will see that once I started mentioning the people on the papers, they actually wrote multiple papers on the components before this as well. Like, this is actually the kind of the last in a very long sequence of chains of papers. Basically, both Yang and Li have been doing this in the last like 3 years or so. So it's a big project. And the other thing is that like there's all these. I mean, most of us are in separate locations. So actually, a lot of it happened via Zoom, and there's actually quite a bit of Discord that happened in here as well. At least for some of the intermediate projects, they were literally organized via Discord. Other questions? Yes, Dennis.
Was there at any point a flash of insight where everything kind of came together into this efficiency of the algorithm? Like you saw the whole picture and go, oh, I have this great idea to put this all together, like a flash of insight. Yeah.
Okay. So the question is, was there kind of like a point where you know this was going to work? So going back a little bit about this, actually, so the last piece that we really knew, well, there was actually 2 things that was actually a little crazy here. The first is that actually to dig up this Walker-Zimmerman. So actually, we were trying to solve some slightly easier version called p-norm flows. So p-norm flow is, again, like it's kind of like a programming contest thing, right? Which instead of, like, you know how many problems you have seen, which is like minimize the sum of squares, or like minimize the sum of fourth powers. Like you have a bunch of convex functions, minimize that. So we're actually working on a more kind of convex version of it until one of the co-authors basically said, hey, like, why don't you just like throw this iterative method at it? And then, like, so a lot of the tools were not actually initially developed to address the max flow problem itself. They were designed to address some intermediate problem. So that was kind of one of the crazy things that happened last October. And then the other crazy thing that happened last November is that we actually designed a data structure that does not exactly work because of the guarantees of the way these things work. So at some point, you actually have to kind of think things very holistically. You have to kind of believe that like every data structure problem has a divide and conquer version. So you know, like basically anytime, for those who have seen plane sweeps, right? Anytime you have a plane sweep, you have a div-conquer variant of that as well. And you kind of have to think a little bit offline for that. And that was kind of the other kind of crazy thing that happened sometime last, I would say, early December. And that took another couple of weeks. And then once that got worked out, it was like, I think at some point by like mid-December, we had a m to the 1.33 algorithm for general mean cost flow. And at that point, it was like pretty clear you were up to something. And then like another month or so after that, it just had to get the whole recursion to work. And that's how the whole kind of thing, like the whole thing we kind of knew we had by like the end of January-ish by that point. Okay. Other questions? Okay. So next, what I want to talk about is I want to go into the technical details. I want to talk about how the pieces are actually talking with each other. So I want to talk a little bit about optimization. I want to talk a little bit about tree data structures. These are probably familiar to you with like all the pieces. Like the kind of the formulation are familiar to you, but you will see that this is being done at a much more kind of abstract and more formal level. So I want to first talk about the fact that iterative algorithms are absolutely magic. So there's this whole kind of thing that we're used to design algorithms that produce you the correct answer at the first step. And then there was this kind of troll paper from, when was this posted? Oh yeah, this was posted 3.5 years ago. Everyone knows the Floyd-Warshall algorithm, right? There are these 3 for loops you use it to set the distance, you use it to compute all pair shortest path. And I'm sure we have all typed the order of those 3 loops wrong, right? It's actually kind of not clear that it's IJK, JKI, and so on. These 2 guys, by the way, who both were double world final participants, prove that no matter how you set the loop ordering, you just take the resulting algorithm, run it on the distance array 3 times. It's going to produce you the correct answer. So there's a kind of very general phenomenon which says that very often you can iterate a kind of a simple or even bad algorithm multiple times and have it converge to the correct answer. And this is kind of like the first thing that you kind of have to really believe that this is possible. And like, I mean, the way you do this, you kind of really believe this is like you either like write the code, you experiment with it. I mean, probably what happened is these guys were trying to to make some data that breaks some solution they didn't like. Chances are that's how they came up with this idea. But you kind of just have to experiment a bunch and then just be aware that this kind of ideas are possible. But once you believe this, the next one may not sound as ridiculous. It says that once you do convex optimization, you can actually get away with using undirected residual graphs. So instead of working with residual graphs that are directed, so for when we code MaxFlow in programming contests, right, we always have to work with a directed graph in the intermediate steps. This result by Daisha and Spielman said something that was very remarkable, which says that you can actually work with undirected residual problems in all intermediate iterations. So you can replace this kind of directed intermediate instance via undirected ones. And the key here is that your intermediate solutions, they actually have more state, right? You have to track like how are they making progress. And the idea is to do this numerically. And this is extremely powerful because we're far, far better at processing undirected graphs than we're processing directed graphs. And this makes a lot of things work. So let me talk a little bit of how do you get to undirected residual graphs, and this requires going into a little bit into the notion of convex optimization. Convex optimization is I have a convex function, I want to minimize it. There are several ways you can do convex optimization. Those who have dabbled in machine learning probably know gradient descent, right? You just take the gradient, walk in that direction, and keep on going. The guarantees of gradient descent isn't as good, in that to produce an epsilon approximate solution, they need something like poly 1 over epsilon iterations. So to actually get the high accuracy solutions that's needed for the overall guarantee in this paper, what we had to do is to use what's called interior point method, which is what's called a second order method, in that you look at not just the gradient, but also the second order Taylor expansion. You look at the Hessian term as well. So here it was very helpful to have a co-author who can just like randomly show up to AdCoder and get rank 30. So this is a co-author on the paper. This is his AdCoder record. He basically just showed up, and then just kept, and his ranking was just like, yeah, like he was basically performing the 3000s level. And he basically over the last couple of years just wrote a lot of, he was working on this kind of like second order optimization for network flows, and these are the papers. So he was the one that first got the 11 over 8, so that's the 1.375. Then he got to 1.33, and then there was some work on a dense instance that got to m plus n to the 1.5 that he also was co-author on. And then there was more, and then we started working going after the actual exponent. So this is going back to Dennis's question of like, how did this kind of happen? And the answer is very gradually. So we first beat 1.5 by 1 over 328. And that was a 70-page paper. And to top it off, then we wrote a 100-page paper that turned the 328 into a 58. And the joke among the 7 of us on the paper was that what is 58? We took the 3 and 2, we added them. So the next paper we should write 1 over 13, and then we should write 1 over 4, and we're going to get stuck at 1.25 with that approach. We still think that approach gets stuck at 1.25, by the way. So this is just to give you an idea that just like, once you start doing these things theoretically, right, you can kind of just gradually build up and understand the mathematics better. But by now, we do understand the mathematics a little better, so let me tell you the end story to this, which is the way you write down this kind of optimization problem is you just define, You let f be the flow values on the edges. You define that, hey, flowing equal flow out at the vertices, they meet demands. And then you define the cost of the flow plus some barrier function. And the barrier function is a function that looks like this curve on the right. It's basically what you use is log of f. And the property you use as this function basically prevents your f from going below 0. It's a function that reaches infinity as f goes to 0. So it basically acts as a wall, and it serves as your linear inequality. Then you go do some multivariate calculus. And after you're finished with the calculus, what you get is that it suffices to repeatedly approximate and minimize the first and second Taylor term. So the first term is gradient times the edge, and then the second term ends up being the current flow value, the change divided by the current flow value, so the relative change, sum of squares of that. So the natural kind of Taylor expansion way of doing this is that you just gradually compute something involving the gradient, and the second order change squares sum together. And to make it easier, the trick is instead of using a sum of squares, use L1. So instead of doing sum of squares, you just take the sum of absolute values. And this is what arrives at the mean ratio cycle problem. So the idea is that instead of having sum of squares, you just take the sum of their absolute values. And you get the mean ratio cycle problem, which is you maximize G transpose delta. Subject to delta is a circulation. And then the sum of the relative changes of delta is at most 1. This is a much more combinatorial problem and has a couple of nice properties, which is that first of all, the optimal solution is always a single cycle. But it has a slightly higher iteration count. So instead of having root n iteration count, now your iteration count becomes n. So your data structure needs to be far, far more efficient. But we like data structures. So the rest of this whole thing is about dynamically approximate a mean ratio cycle. So formally, you want to support changes in G, changes in F, and then outputting the mean ratio cycle and updating the current flow with it. So that ends up being the data structure. Yes, question? Sorry? Oh, what's the bracket notation like the G delta? That's inner product of vectors. So these are all just vectors. So that what they are is just inner product of A and B is summing over I of AI, BI. You just take the pairwise product of all the things, you add them together. It's like how you compute the cost of a flow. Okay? And this is where we get to tree data structures. So I'm about to go into trees, which is something that we're all pretty familiar with. But before I go into actual trees, I do want to say that there's actually a kind of tree that you're not very familiar with. So we have seen things like BFS tree, DFS tree. We have seen a shortest path tree, minimum weight spanning tree. The tree that you probably have not heard about is what's called a low stretch spanning tree. A low stretch spanning tree is a tree such that the average distortion, so in expectation, the distortion of an edge is something like log n. So you can show that for undirected graphs, given any undirected graph, you can always find a random tree such that the average distortion of an edge is not very large. And then the algorithm becomes sample a random tree, return the best tree cycle, and then just look at that answer. Yes, Andrew? Oh, what is the distortion of an edge? Okay, I will get to that formally on the next. So what you get is that you let the, for every non-tree edge, you consider a non-tree edge E. What you get is that the length of the tree cycle in expectation is less than n to the little of 1 of the length of the edge itself. And you can prove this exists for any undirected graph, and that's kind of the critical reason we use undirected graphs, is that undirected graphs, up to some approximation, are fundamentally tree-like. How do we manipulate this? So then now we say that let the optimal mean ratio cycle be delta star. Apply the linearity of expectation on that. What you get is that you get a sum over all the edges of on the optimal cycle. You get that length is less or equal to n to the little of 1 of the length of that cycle. And then now you do linearity of expectation, you move it outside. And now you do Markov. Markov says that with probability of half, you're going to get a tree where this is true. So you get that with probability of half, a random tree is going to give you one where, with probability of half, if you generate such trees at random, you get that the distortion, the length of the cycle against that tree is less or equal to some small factor times the actual length. And then the main thing is that the gradient term, because the gradient term is just a dot product. If I traverse it forward, backwards along a tree edge, it's going to cancel. So if I look at the gradient and how the tree affects the gradient, that's all going to become 0. So what I get is actually the gradient cancels, which means that if I look at the average over all the edges on the cycle, you actually get that the best off-tree edge is going to give you something that is good. This is the point where you switch over to the tree data structure view of things, and now you just do a dynamic approximate mean ratio cycle. So the idea is instead of working with trees, you work with partial trees. You work with trees with a couple of extra vertices. You work with, instead of a recursion, you say that I want my reduction factor to be n to the little of 1. You pick some extra vertices. You get a partial tree maintenance. And then the main thing is how doing the recursion, and then bounding how much each change on one level affects the next level. Like, this is the point where all the seg tree way of thinking of the world comes in. And yeah, here it was helpful to have an author who really a co-author who really liked trees. So Lee basically showed up, did ICPC with us, and then just wrote nothing but papers on dynamic heavy light decompositions, centroid decompositions, and more tree decompositions. So he first wrote about how the Madre scheme can be made approximate. Then he did L2 diffusion on trees via propagating convex functions. This is actually kind of the dual way to solve World Final 2018 problem C. And then there's this flow paper, and then in progress there's some stuff about combining learning with data structures. The rough idea of how this works is that you work with what's called a partial tree. So this is a tree, this is a forest. Instead of a tree, you have a forest. And then you have this partial tree where the roots are vertices of the smaller graph. So given a graph and a partial tree, what you do, you contract the trees. You turn each tree into a single vertex. And that's called vertex sparsification. Now you get to a smaller graph. And the key thing now is that if I define a partial tree to be a tree plus, with a tree removing at most something like m over k edges, where k is my recursion reduction factor, what I get is I get a problem whose size is smaller by a factor of k. So the vertex count decreases by a factor of k. And this is what we call the core graph. And then there's another tool, which is called graph sparsification. This is the idea that most undirected graphs have sparse approximations. So instead of working with m edges, now you work with m over k edges. And now you're onto the next level recursion problem, where the problem size is now something like m over k. And then as you can imagine, the main difficulty of getting this whole thing to work is how does this work recursively, right? The idea is what happens if I change my original graph, what happens to the lower level? So here I have an example where there are 3 pieces to the tree, and then in the contracted core graph, there's a 3-vertex graph. What happens if I delete an edge from G? What happens if I delete one of the edges belonging to a tree from G? What happens here is that instead of having a single tree, now it's 2 trees. In other words, this is a vertex split. So you have to remove it from the forest, it becomes 2 pieces, and what you get is instead of 1 vertex, it becomes 2 vertices. So kind of the crux of the difficulty is we have to design dynamic graph algorithms that work against turning a vertex, that works under the operation of taking a vertex, splitting it. So you actually, it's kind of like unifying, but thinking in the opposite direction, but also along a tree. So at the end of the day, what we show is that it's possible to have a sparsification data structure such that each vertex split, each vertex split becomes a small number of edge splits, of edge updates in the resulting sparsifier. And the critical thing is that this increase in reduction, this increase in the number of changes in the next level has nothing to do with k, which is the reduction factor. And then this kind of decoupling of k and the amount of changes that happen in the next level lets the whole thing go through. And by saying the whole thing goes through, I'm actually hiding another major detail, which is, I think this is the point where programming context knowledge actually helped the most. In that there's actually kind of this issue with everything I talked about, which is that the tree that I said, right? I said I'm finding a random tree. I'm using expectation. This is all assuming that my trees generate independently of my input. There's actually like a lot of independence. Like it's assuming that I'm dealing with formally what's called an oblivious adversary. But the issue is that my data structure is being updated by its output. So its output actually makes the data structure dependent of its own input. So you actually break this independence assumption in the analysis of the data structure. And this is the point where somehow being able to view this kind of thing holistically and getting used to this kind of way we think about data structures kind of in a batched manner in programming competitions, this was extremely useful. In that, what we ended up doing is we showed that we analyzed the data structure not against any kind of arbitrary solution. We analyzed against f star minus f. So we analyzed against the optimum update step of the convex optimization data structure. And we showed that the only places where f star minus f can change significantly are precisely the edges that's being updated. So what we did is we kind of say that when an edge gets updated, you go back to that piece, you rebuild it, completely reinitialize the randomization. And then, but for the things you haven't touched, the f star minus f is roughly stable, and then everything is okay there as well. So that's all I can really say about the data structure in the limited time I have. In the remaining time, I want to talk a little bit about what's happening now and how I think about this. How am I doing for time? I actually don't have a clock on me. Huh? 10 minutes. Okay. It's 11:50 right now. Okay, cool. Okay. So what I'll do is I'll quickly go through kind of current state of things in 5 minutes, and I'll start doing a Q&A. I actually want to do a bit of a Q&A because there's a kind of a lot of both technical and non-technical things being covered here. So we posted a paper that's got picked up by Codeforces right away. So there was also a bit of a discussion on Codeforces where Yang essentially talked through his take on the convex optimization and undirected residual graphs. Got quite a bit of questions about can we code this? And the answer is you probably don't want to code this because the actual runtime of the algorithm is something like exp, so the m to the little of 1 is exp of log n log n to the power of 7/8. So if you ignore all constants, which is, I mean, it's a big assumption here, but even if you ignore all constants, this is not going to be better than n for any n that's less than something like 2 to the 40 or something like that. So it's a completely theoretical style algorithm, but you can indeed prove that this is a runtime that is less than m to the little of 1. So the way that I really like, I once heard a description of what such algorithms are from a collaborator, and I really like this description, which is that this result is more of an indication that there might be good algorithms using some of these ideas rather than a standalone algorithm. And this is kind of the state of algorithms research, is that some of these things just take so much work to develop that, I mean, this is showing that maybe somewhere along here, something good happens. Like we can get a very practical, very usable code. But right now, it's really just a kind of a mathematical proof of concept that some combination of these ideas is indeed enough to go very far with proving bounds. It does also say that trees and convexity are indeed very useful concepts, and we should probably ask them more in programming contests. It also says that for a lot of problems that we are familiar with, we can probably prove far better theoretical bounds. So I think that's kind of really the main takeaways from this algorithm. I do want to also, but on the other hand, because I'm kind of coming from academic background, I do want to also give you just to give you a quick taste of like how I try to sell this to someone doing algorithms research. So one of the kind of the direct motivations is just we have lots of large graphs, right? We have a lot of very large graphs. So we started off with the Euler problem, right? There is, like Euler tour is very magical in that it's a linear time algorithm. And then as things get bigger, dynamic data, large, say a billion edges, this gets increasingly important as well. The motivation from optimization is that we started off by studying things like matching, flows, and so on. But with a kind of modern data sets, there's probability, it's fuzzy. So we have things like routings, auctions, we have like Wasserstein GANs, where you're actually using these things called optimal transport, which is basically bipartite matching inside learning algorithms. So there's actually a lot of these kind of very fuzzy problems. And the question is maybe we should we should study a lot of kind of these kind of more kind of fuzzy kind of mean ratio cycle type problems. And then from a data structure point of view, right, data structures, things like dynamic trees, splay trees, link cut trees, suffix arrays, they're all for very very well-defined combinatorial problems. But nowadays with approximation, we're using them with optimization, we're doing them with randomization. So once you put all these pieces in there, you got a much richer and much more complicated space. For some of you who have, I'm not sure how many are familiar with this, but there's actually a lot of recent work in data structures about getting data structures to work with these more kind of fuzzy constraints. So for example, recently there are also some work on things like dynamic suffix trees and the dynamic string matching. So, and then going back to the question about can I code this? The flow problem itself is actually not that useful in that chances are a lot of the flow problems we have right now, you just go solve a linear program, solve an integer program, it works just as well. But on the other hand, there are a lot of applications that solve essentially very large instances of these graph optimization problems. So I actually put down the formulation. What it is, you're just minimizing some convex objective on the edges, and then the dual is I have labels on vertices, I minimize some function on the difference of labels on the vertices. These things show up in things like VLSI design, routing, auction, clustering, image processing, even planarity testing. You have these actually show up all over the place. So for those who actually want to do this kind of from a more kind of experimental / implementation point of view, the problems I suggest you look up are things like optimal transport, learning on graphs. So the Open Graph Benchmark actually runs like regular challenges about how to properly label and do link prediction on graphs. And if you prefer kind of a more kind of setting that's kind of closer to like I have an input file, I have an output file, kind of more the batch format, like combinatorial. There are all this kind of work on doing large-scale graph in parallel. So kind of the idea is that you have a 64-core machine or 128-core machine. How do you scale such algorithms without, how do you get a linear speed up from the number of processors to the speed of algorithms? And there you can actually work kind of more closely to a more theoretically provable envelope as well. For the more theoretical side, questions that are kind of natural, but I will cut short on this, is maybe can we do this for general graph matching as well? What about dynamic graphs? So dynamic graphs, this is actually a very funny one in that currently there's a 90-page paper on arXiv about how to get dynamic 10-edge connectivity. So this is the problem of insert an edge, delete an edge, check if S and T is 10-edge connected. So that is the maximum flow from S to T at least 10, or for some small value C. This is kind of one of the things about this kind of modern tool set that I think really can use some very simple, very neat insights as well. So that's also a problem that I highly recommend you look into. But finally, I want to give you a bit of my take on this kind of connection between programming competitions and algorithms research. I'm actually fairly active on a website called dmodge.ca, which is the Canadian high school coding website. They have a Discord, and they actually have a channel, which you can join by clicking the penguin sign. It's called RPen Rants. So the way that I like to say this is that after you get to about Codeforce's AdCoder rating about 2200, what you're really learning in getting better at programming contests is you're really learning skills that's primarily skills from algorithms research. So that's kind of so once you're past that point and you enjoy things, I think you really should try doing some algorithms research. In fact, from my talk with research colleagues, I find that a lot of the techniques or ideas from programming contests are actually very often underrated, especially when it's a problem that a lot of people have thought about, but none of the people who have thought about that problem in particular are familiar with programming contest ideas. On the other hand, going back to the programming contest side of things, I also consider it to be that actually we spend a lot of time coaching contestants to become better at programming contests, but we don't spend as much time coaching contestants on how to transfer the ideas of what they know outside of programming contests. So one thing that I feel is very underrated is kind of some kind of knowledge in how to move on from programming competitions. About that one idea in particular, one thing that I've noticed is that actually a major obstacle in moving into research for programming contest people is actually seems to be getting past the initial admissions stage. But here, I mean, so this is just something to be aware of, that because they do speak different languages, so that you have to be very careful when doing the initial applications just to make sure that you do talk to the right people who work on these kind of more algorithm side of research. Here, I mean, maybe we can just talk about this after, but actually raise your hand if you're looking, if you have if you are supervising PhD students doing some kind of algorithms research. I mean, here you can definitely talk with Jelani about this. You can definitely talk with Pavel Gabrielowski about it. I see Zach over there as well. And yeah, so I'm sure there are plenty of people you can talk with about it. And otherwise, we can do this either in the Q&A or you can also get on the Discord. I'll be happy to talk with you more there as well. Okay, that's all I have to say. Thank you for listening.